Greetings, it's Paul Bamberg with the introductory video for Class 21 of Math 117. This will be a little bit redundant with the previous class, but this topic is so tricky I think that a little redundancy is probably a good idea. So previously we have been studying simple models either for scratch tickets where we don't have to worry about gaining any significant amount of interest because the periods of time are so short, or for companies where we do have to take compound interest into account. And we made two simplifying assumptions, both of them quite unrealistic. The first one was that the share price is well defined and shares can be traded only at a finite number of specified times. Once a day in the case of scratch tickets, and as I recall, once a year in the case of the Sons of Jacob grain storage. Furthermore, at each of those times, the share price is a simple random variable. It can take on only one of a finite number of possible values, and given the price at one time, the price either goes up or down by a specified amount. There are only two possibilities for the price at the next time. We're going to get rid of both these problems at once by saying that the share price is a random variable x sub t. It's indexed by a real number t a time, and it is no longer simple. It can take on any positive value. Now, we've been using all throughout the course the fact that the balance in a bank account grows exponentially like e to the rt. So it's not unreasonable to assume, even if there's no random element to the evolution of time, that a share value might rise exponentially. It might be x naught times e to the mu t equals x sub t. In fact, if there's no randomness and we want the discounted future value to be a martingale, we will have to make it rise with mu equal to r in order to make the discounted value stay constant. And we learned last time in looking at the binomial model that it's a strange feature of the binomial model that you have to introduce a little bit of drift in order to compensate for the fact that if shares either go up by multiplication by some number or down by division by that same number, the expected value tends to go up, and for a martingale we have to compensate for that. We also found in the binomial model we could compensate for most any drift we introduced by simply adjusting the risk-neutral probabilities. Suppose that we have a share that's priced at 40. It might split into two shares priced at 20, and if the value of the company increases by 5%, shares that would have gone from 40 to 42 would go from 20 to 21. In other words, it's realistic for stock prices to assume that the changes are proportional to the current value of the shares. It might be that the pricing is a result of the view of investors, but if Potiphar looks at his shares in Sons of Jacob grain storage and says, the Nile flood doesn't look very good this year, I think these shares look worth 42 instead of 40. If they'd split, he'd say, yeah, they look worth 21 instead of 20. What this means is that we're going to add our random share prices not to the share price, but to the exponent. We did that last time in the binomial problem, so it should be familiar to you. And our model is going to be that x sub t, the share value at time t, is equal to x naught, the value at x0, multiplied by the exponential of mu t, a drift which is purely deterministic, plus z sub t, a random component. And we've already addressed the problem that arises if we say a share is equally likely to double in value or halve in value, and if each of those things happens 50% of the time, the expected value will go up. We can address this issue without changing the probability of going up from 1/2 by introducing a drift, and we know what the right drift is. The drift is mu equals minus sigma squared over 2 times t, because we know that if we add that in the exponent to sigma times omega sub t, we created a martingale. We proved that a couple of weeks ago. Now, w sub t is the sum of changes which equal plus or minus 1. Its variance is t. But realistically, we don't want such large changes in the exponent. We only want changes that are proportional to t. So we will set z sub t equal to sigma times w sub t. Multiplying by sigma multiplies the variance by sigma squared, and the variance of the random component z sub t is therefore going to be sigma squared times t. Now you've already seen the binomial model. We'll achieve our n steps today, and I'm going to use little n because I want to use capital N today to symbolize the normal distribution. I'm going to break up a time interval t into n steps, and the length of each of those, t over n, I will denote by delta t. In one of these steps, wt either goes up by some amount delta x or decreases by delta x. The variance is clearly delta x squared because delta x squared has a constant value. If we have n independent steps, the variance is going to be n times delta x squared, and we know that the variance has to be proportional to the time interval, so that has to equal n times delta t. That means if we make the change delta x squared equal to the time interval delta t, then the sum of these random changes will approach a normal distribution with variance t and expectation 0 in the limit when n gets very large. If you think about this, you see that delta x over delta t is going to keep getting larger as n approaches infinity. That's going to manifest itself in the fact that our paths will turn out to be almost surely continuous and almost surely not differentiable at every point. So we've created a model with the following properties. W sub 0 starts out at 0. It sits there in the exponent doing nothing. W sub t is normally distributed with expectation 0 and variance t. You've already done some martingale calculations involving that. If we consider two time intervals, one from t1 to t2 and one from t3 to t4, what happens in the second time interval is independent of what happened in the first time interval. You've dealt with that in proving martingale properties. If you ask for the probability distribution for w sub t minus w sub s, the change in the exponent over the interval from s to t, that's normally distributed. It depends only on the length of the interval, and the variance is t minus s. And finally, the share price in this model is the price at time 0, x0, times the expectation of mu t, the drift part, plus sigma times wt, the random walk part. This is historically known as Brownian motion because it arose first in physics, was studied by Einstein, in fact. It's also known as a Wiener process. That's not Anthony Wiener, it's the famous Norbert Wiener. Now you might worry about what the probability space is. And that's really worth worrying about, though I'm not going to give you a very satisfactory answer. If I stick with the binomial model and simply break a time interval into n equal intervals, then I've only got a finite number of them, no matter how small the intervals may become, and I'm dealing with the product measure on a sample space that's Rn. But if I take the limit, then the sample space has infinite dimension. In fact, it has uncountably infinite dimension. It's R for the interval from 0 to infinity, which is an uncountably infinite set. And as I said, the paths that we find in this sample space, I'm not going to prove this, are almost surely continuous, but almost surely not differentiable. What does W sub t do on this sample space? Well, an element of the sample space is a function of time, gives share price as a function of time, continuous, though probably not differentiable. And what W sub t does is simply to extract the share price at time little t. The probability measure on this space has to be an infinite product, and it is called capital W, W from Wiener, and we are not going to fuss about the mathematical technicalities of this product probability measure. Now we've got to fix the martingale property in the exponent. If you look at the discounted future value of a share, I've multiplied by e to the minus rt in order to discount the future value. That's a random variable, but as we found out last time, it's not necessarily a martingale. We have to have just the right value for the drift, and in this case, we need some drift in order to offset the discounting effect. So it's mu minus r that has to equal 1/2 sigma squared. So one way of dealing with this problem is to introduce the right drift. Another way of doing it, which was the approach we took last time, is we will redefine the probability measure so that the discounted future value is a martingale. That is, given a certain drift specified by mu, we will simply adjust the probability of an up step in such a way that the expected share price doesn't change with time. Now we can start thinking about how to price a call option. We're creating the same sort of risk-neutral probability measure that we did with the binomial distribution last time. We're going to change the probability for the share price to rise from 1/2 to some appropriate value, which we'll call p. And we know that p will equal 1/2 if the drift happens to equal r minus 1/2 sigma squared. You shouldn't be too surprised that the amount by which the probability exceeds 1/2 is r minus mu minus sigma squared over 2 sigma times delta x. In fact, you proved that result last time for the special case where r was equal to 0. So we're making our random walk a little bit unsymmetric. The probability of an up step is different from the probability for a down step. That's a phenomenon that you're already familiar with for the binomial model. Following Deneen, let's notate it by A super n sub j. That is what happens in step j out of n steps. And we know what's going to happen in the jth time interval delta t. The price will go up by sigma times delta x with probability p, down by the same amount with probability 1 minus p, and it's easy to calculate the expectation. The expectation turns out to be r minus mu minus sigma squared over 2 divided by 2 sigma multiplied by delta x squared. This is the phenomenon with which you're already familiar that if the exponent goes up or down by the same amount, the share price tends to drift by an amount that's proportional to delta x squared. Now the change in the exponent is always sigma times delta x, no matter whether it's up or down. So its square is a constant, and we know the expectation of the square. The expectation is very close to 0, so while strictly speaking, the variance is the expectation of the square minus the square of the expectation. We can forget about the square of the expectation for small delta x and say we also know the variance of this. If we sum over all these short intervals, we still get the same variance as before, but we now know the expectation of the sum of the variances. It's r minus mu minus sigma squared over 2 divided by 2 sigma times t, proportional to t as before. Now we've succeeded in making the discounted share price e to the minus rt times x sub t a martingale with respect to this new probability distribution, and since we know it's a martingale, we can calculate the fair price. All we have to do is look at situations where the price at time t exceeds the strike price k, take the expectation of that with respect to a probability distribution which we now know, and using the martingale property we can say the result is the share price, the fair price of the option at time 0. Next time I will work out the details of this and we will end up with the Black-Scholes option pricing formula. But before doing that, I want to introduce call options in a simpler context. Let's consider how we might have a call option for casino gambling. So say the casino owner is worried that you're going to break the bank, and he offers to sell you an option that will let him purchase your stack of chips for K dollars just before you cash them in. What's the fair price of this option? Well, suppose you're planning to leave after T spins of the wheel. The fair price of this option, before you ever start playing, is the expectation of your stack of chips at time t minus the strike price k, with the expectation taken only over positive values. For small values of t, you can work this out by brute force, but you can't do it in general. However, you've already seen this martingale convergence trick. If you're not planning to leave at a specific time, but are instead planning to stick around until you either go broke or end up with M chips, then there is a limiting random variable, x sub infinity, whose value is almost surely either M or 0. It's not impossible that you could play in the casino forever without either reaching your goal or going broke, but the probability of that event is 0. So in a casino, we can just compute the expectation of the positive part of x infinity minus the strike price k. That'll give us a fair price for an option. Previously, with options, in addition to taking the buyer's point of view, which I've just described, we've also taken the seller's point of view. Suppose you've sold a call option to a bettor, and this bettor is looking awfully lucky. If the bettor is lucky, then his stake is going to go way up, and you're going to have to pay a lot to settle this option. How do you hedge your position? Well, you start betting the same way the bettor is going, so that if he's lucky, you'll be lucky too. If he seems likely to go broke, then this option is almost certainly worthless, and there's no need to bet. So what you probably want to do is make the amount you bet be higher when the bettor is doing well, make it lower when the bettor is doing badly. And this is similar to a strategy you've encountered earlier, where if you're using shares to hedge a call option that you have sold, you hold more shares if the option seems more likely to be in the money. I want to conclude with some interesting quotes from Casanova that I found in Grumet and Sturzaker's textbook. Back in 1754, Casanova himself was playing the martingale. Playing the martingale, constantly doubling my stake, I won every day during the rest of the carnival. I was fortunate enough never to lose the sixth card, and if I had lost it, I should have been without money to play, for I had 2,000 sequins on that card. I congratulated myself on having increased the fortune of my dear mistress, presumably by 1 sequin at a time, and Casanova clearly appreciates the peril of the traditional martingale. But not in time. A few days later, I still played the martingale, but with such bad luck that I was soon left without a sequin. As I shared my property with my mistress, I was obliged to tell her of my losses, and at her request sold all her diamonds, losing what I got for them. She now had only 500 sequins. There was no more talk of her escaping from the convent, for we had nothing to live on. Presumably Casanova just went off and found another mistress, but he will figure prominently in some of our casino gambling scenarios in the group problems.